Okay, so you can turn in your homework during the first and second class, okay? Don't worry about that if you have problems. By the end of the second section, we will have the first quiz, okay? Let's see, I will give you at least 20 minutes. So I believe many of you guys can finish in about 10 minutes or so. If there's no problem for you to do the homework, so don't worry about that, okay? Currently, for the arrangement for the next few weeks, we know that the midterm is about 3 weeks away, right? So it's on the 13th in class. Today I'm going to finish chapter 4, start chapter 5, briefly talk about chapter 5. Next week, I should finish chapter 5, and then on the 6th, October 6th, there will be another second quiz, okay? That will cover chapter 4 and 5. So you will see from my presentations, not all chapter 4 and 5 are actually covered. I only can cover part of those, okay? So only those show up, the contents show up in the presentation. Those will be covered, that could be covered in the quiz and also in the exam, okay? So don't forget, October 6th, there's another quiz, okay? Cover chapter 4 and 5. And then next week and the 6th, I'm going to start chapter 6. Chapter 6 is very important, okay? So the first exam will cover all the contents up to October 6th. Okay, anything we talk about before that could be covered in the first exam. Okay? So any question regarding this arrangement? If not, then I want to go, the first lecture, I want to finish chapter 4. Okay? So last class, we talked about solidification, right? Today we will focus on the defects, the crystal defects. I want to go very quickly, okay, to let you refresh what we learned in last class. So when we talk about the liquids, when they're cooling down to generate solid, we know that now we talk about metals, okay? They also works for semiconductors. So first, the small seeds, right? When they have a size above the critical size, then they will grow. These seeds will grow, right? Then each seed could grow to a grain, and later on, between the single domain grains, you will see these kind of grain boundaries, right? So that's what we learned at the beginning. And also we know that the simplest way to think about the crystalline or the solidification is homogeneous nucleation, right? So in that case, last class we talked about the two contributions, right? One is a free energy related to the phase change from the liquid to the solid, right? So we know that this process will release heat. So that means they will promote, okay, these will provide the energy for the solidification to occur, right? But there's retardant or there's another resistance against this crystallization or the solidification is because when you generate solid domains, those solid domains will have surface areas. You have to compensate the energy you need to generate new surfaces, right? The surface here I mentioned is the solid and the liquid interface. Okay, so those will be the surface term, which is the retardance or which is the resistance. So this kind of a curve, I hope you guys understand that one, very commonly used, okay, in chemical engineering and also in physics. So here, when we consider the overall process, there are two contributions, right? One is related to the surface energy, which is always a positive. Another one is the solidification caused by the phase change, which is always because it's a exothermic process, so it's release heat. When you combine those, you will see a curve like that. There's a maximum upon there. Okay, this maximum pump corresponding to a size. We call that size critical size. The reason for that is because when the size is smaller than that, you will say the energy will go downhill. So that means when a crystal, when a seed has a size below this critical size, what they tend to go, they will tend to go downhill. So that means they tend to dissolve. Okay. Otherwise, if they're above that one, from the energy consideration, they will go this way. So that means the states will go bigger. Okay. So that's easy to understand, right? Okay. So as I mentioned, when you talk about the critical size affected by several parameters. Okay. The most important thing is the delta T. Supercooling. Okay. So that means how much difference, the temperature difference between the melting pump and the cooling pump. The larger delta T, you will say you need a smaller R star, right? So that means when you have a larger, undercooling, that means the cooling process or the solidification process will be easier because you do not need a very large, the seed size. Right? So yeah, with that.
On the slide before, if you do like perfectly at R star, does it go right?
You mean about here?
Yeah, if you seed it perfectly at R star, will it go left or it just stays there?
Oh, you mean just at R star? Oh, this is just a conceptual. It could be either way. Okay, if just exactly this way, it could be either way. Thermodynamically, it's kind of like an energy theory. But which way they will go mostly determined by the kinetics. Okay, but they can go either way. Beside delta T, also the delta HF, which is the latent heat of fusion. That one, don't forget about that one. This one is enhancement term. They will improve the solidification, right? So therefore, if this one is larger, also the solidification process will be easier. But against this one, if the surface tension term, which is retardance term, when that one is larger, you need a larger R star. Easy to understand, right? Seems for the melting temperature, when the metal is harder to melt, that means you also need a larger critical size, right? And the reason why that the heterogeneous nucleation usually happens instead of the homogeneous one is because when you have like a impurity surface and your liquid and your metal liquids can wet the surface, they prefer to condense on this kind of impurity surface first because they will reduce the overall surface energy. Okay, so that's the reason why heterogeneous nucleation occurs more frequently than the homogeneous one. And also we know about when the seeds grow, they grow to the single domain. Each of that is a single domain. Okay, so that means they're a micro-scale single crystal. But between them, when they have green boundaries, means what? Means they have a different orientation. Okay? So, and also we can control in the real industrial process, we can control usually the delta T, and then we will get a different crystallization geometry. And also we talk about, later on when we talk about chapter 6, if you are concerned about the mechanical property of the metals, you might prefer the finer domains. Okay, the reason for that is because if you are using the same metal, but one has this kind of a large domain, one has a small domain, this one usually have a better mechanical property. They are stronger. Okay, so in chapter 6, I will explain why that happens. So to generate these kind of finer domains, usually what you do, you add in some like a seed particle, or sometimes you could even add some impurity particle inside, okay, to induce the formation of the smaller domain. And by the end of last class, we talked about the silicon wafer, not only the metal process, but also for the silicon process, you use a seed, which is a single crystal seed, to induce, when you withdraw this rod, a small rod-shaped single crystals out of silicon melt. What you will get, you will induce the formation of a single crystal silicon. And then later on, you can cut this, this rod to generate those kind of silicon wafers. Okay, silicon wafer later on you will say, those are very useful for semiconductor fabrications. Okay, so that's what covered in last class. But don't forget, in reality, not only single metals. In many cases, most of the applications when we deal with metals, we are talking about alloys, okay? Because alloys usually have much better, have improved properties. They could be more resistant, to the corrosion. They could have much improved mechanical strength. Okay, so when we talk about the metals, the simplest case we can think about is a solid solution. So that means when you have two or more different metals, when you melting them together and then cooling down, later on you have only a single phase, so they will form a solid solution. So solid solution is the simplest form of alloy. Okay, so it's easy to understand. Some examples of alloys, for example, when we talk about brass, which is a simple, two component, 70% of a copper, 30% of zinc. Mixing them to a single phase, you get a brass. Okay, so which is stronger than both of the zinc and the copper components. And also, if you think about the Inconel, which is also widely used in engineering alloy, can be used for, say, for example, the airplanes. Some important part of airplanes you need the Inconel, which is a nickel-based alloy. We call that super alloy. I will tell you why, okay, later. I think a very unique property. So that alloy, most of the components is nickel, but we also have many other elements, including like a chromium, iron, carbon, and some others, okay? So that will make the mechanical property of the Inconel really desirable for many applications, okay? So when we talk about the solid solution, because solid solution is easy to understand. Okay, so it's a single phase. So the commonly used type, we call that the substitutional solid solution. So that means when you have two metals, okay, the atom size are very similar to each other. And also these different metals, their crystal structure are similar, or ideally they should be the same, okay? So in that case, then they will kind of like mix very well each other to form a real like a solution line. Okay, because each of these atoms, though they are different, but they're very similar regarding their chemical property, physical size, as well as their crystal structure. Okay? In that case, they kind of like an interchangeable, so they will form a solution. They will form like a liquid solution line. We call these kind of a small amount, the doping atoms, we call them solvent, similar to the liquid solution. And then the matrix, the majority component of this kind of a binary, or could be more than two different metals. We call those are the solvent, okay, similar to the liquid solution concept, okay? So indeed, the solutes could be, because they have very similar property, if they're almost identical, the next slide I will show you, the percentage of this impurity, or you can call them impurity, or the dopants, for those kind of secondary components, or the solvent, or the solutes, they could change from like a very small amount to up to like 100%. So that means you have a broad range of this kind of mixing of that. Okay? So, and the sense that will affect the solubility to form this kind of a very homogeneous alloy, especially for the substitutional compounds. One thing important is surely their diameter, right? So you prefer their diameter change is less than 15%. So that means they're almost the same. So they were not, if there's a large difference in their size, you can easily think about that one. They could generate a lot of defects inside the crystal, right? And also the defects were generated stress. They were destabilized the metal. So the first thing very easy to understand, their size need to be similar, right? That's the first requirement. And also, we prefer they have similar crystal structure. If they are both, if one is FCC, another is FCC, then they will be preferred. But if one is FCC, one is BCC, their packing density are different, right? Don't forget about that. So that could affect the alloying process. Another one, you do not want them to have too much difference in electronegatiivity. Otherwise, if there's too large, remember when we talked about chapter 2, when the electronegatiivity between two metals or one metal and a non-metal are too large, they will react chemically, right? So therefore, their electronegatiivity difference should also not be too large. Otherwise, chemical reaction occurs. Okay, they will form new molecules instead of these atoms, right? So, and also, preferentially, they have the same valence. So if they have 2+, they should both have 2+. Okay, so charges. So some example here, you know, when you think about the copper zinc, which forms the brass in the brass case, their radius difference 3.9%. The electronegatiivity change difference between copper and zinc is small. Their largest solubility you can achieve is about 38%. So the reason for that is because this atomic diameter difference is reasonably large. Okay, one is even larger for the copper lead case, 36% difference, and though there's also a slightly larger difference in the electronegatiivity, but there's only copper, you know, the lead can dissolve in the copper only in like below 1%. So that means they are really, because of the size difference, they are really not alloying together very well. But for the copper and the nickel case, because the size difference are so small, very small, and there's no difference in the electronegatiivity, so they can be made to the whatever level you want. Okay, could up to like 100%. So they are alloying very well. Okay, so in addition to those kind of a similar size atoms, we call them substitutional solid solution. If the size of the solvent and the solute are very different, okay, in that case, the small atom could fill in the interstitial formed by this kind of a larger atoms, right? Easy to understand. In that case, we call them interstitial solid solution. Okay, so usually we need a very large difference. One example, widely used example is in the gamma iron. When we talk about the chapter 3, we know that at a special temperature range, when iron will be in the FCC structure. Okay, below that temperature, they will be the BCC. Remember, above this temperature, they will be in another BCC state. We call them, alpha, beta, gamma iron, right? But in the if the iron is in the FCC range, when the temperature is in this temperature range, so the carbon, in that case, carbon has a radius about 0.75 angstrom, which is significantly smaller than iron, which is 1.29 angstrom size. So, huge difference. In that case, the carbon atom will fill in the interstitials formed by the iron FCC crystal atoms. Okay, so and also you could reach about 2.8% of the carbon can be filled in those interstitial sites. And one thing I want to mention, you can actually easily calculate the interstitial volume. Okay, you can find the size of the atom that can perfectly fit into that space because we know the FCC structure, right? Based on what we learned in chapter 3, we should easily calculate that. But indeed, you will find this size is larger than that. It's larger than the interstitial size. Okay, so therefore, what really happens is the carbon will fill in the interstitials between the iron atoms, but they will deform. They have to deform the atoms of the iron, otherwise it cannot fit in. Okay, so